Greeting, ladies and gentlemen. Today video I'm gonna continue our discussion upon question 6. Under the same subtopic, first law of thermodynamic, open system. Air is compressed from 100 kPa and 22 degrees C to a pressure of 1 megapascal, while being cooled at the rate of 16 kJ per kg. Circulating water through the condenser casing. The volume flow rate of the air at the inlet condition is 150 meter cube per minute. And the power input to the compressor it is 500 kilowatt. Determine A, the mass flow rate of the air. So this is the problem solving. I'm draw the schematic diagram for the compressor. Maybe if you refer to some textbook, the diagram will be differ from me a little bit, but as long as for me, I understand what the situation that I'm dealing with, it is good enough. So we'll have in that we have an outlet. We'll have a work in, since that it is a compressor. We require work in to increase the pressure. In this case, it is air. So we have a property of the air in the inlet that will be at 100 kPa. Temperature will be 22 degrees C. Specific volume 150 meter cube per minute. And indeed, because it is a steady flow, the cannot say that if it is a uncompressible flow, maybe. But anyway, we have a power in 500 kilowatt. And the property of the air at the outlet will be 1 megapascal. Will have a heat loss 16 kilojoule per kg. So since that it is a steady flow, mass flow rate in equal to mass flow rate out equal to rho VA. This is also equal to specific volume, the power of -1 times by V times by A. This equation also can be derived in the form of volume flow rate, which is mass flow rate equal to rho V dot that refer to volume flow rate equal to specific volume, the power of -1 times by the volume flow rate, since that the question given us by volume flow rate. So we can use the gas constant equation to calculate the specific volume, since that we were dealing with air. Remember, if you want to use the gas constant equation, the fluid must be in the form of gas. If it is in the form of saturated, you cannot do so, because a part of it in the form of gas and another it is the liquid. So it is not gonna bring you the right final answer. But anyway, the specific volume we can derive as RT over by P. R is referred to gas constant. For air, there will be 0.2870. You need to include K right there. Times by 295. Temperature air in the inlet, that will be in the form of Kelvin, 22 degrees C, times by 273. We will get 295 over by the pressure in the inlet and 100 K. And you need to include K. So specific volume we will get close to 0.8467 meter cube per kg. So that is the specific volume. So we include in this equation 0.8467, the power of -1, times by the volume flow rate 115 meter cube per minute. You need to convert into SI unit. Otherwise, I think that it is depend on the condition, because for me, it is my habit to change it into SI. I think that if you're not going to change it into SI unit, it is fine. Otherwise, the question telling us so. But in this case, I'm changing into SI unit. That's why I'm divided by 16. So we'll get something like 2.9528 kg per second. So question 2 asking the temperature of the compressor of the air at the exit compressor. We can know the temperature by the enthalpy. So our mission is to find out the enthalpy at the outlet. In this equation, I'm denoted as enthalpy 2. we can know it from the conservation of energy equation. Energy in, specific energy in equal to specific energy out. Why do I'm using the specific? It is because if you look at the table, the value of an energy that will be in the form of kilojoule per kg. Pure energy unit will be only joule. But that's why I'm saying that it is a specific. It is per kg. Maybe if you refer to the another textbook, it will more prefer in using energy in. But for me, I'm just stated as the specific energy. So we'll have a specific energy in the inlet. There will be enthalpy 1 plus by kinetic plus by potential energy. Since that it is a compressor, thus will require the work in on the system, specific work in, and being stated in the equation, being cool at the rate of 16 kilojoule per kg. So this means the system will have a heat loss. So that's why we will minus it by Q dot equal to enthalpy 2 plus by kinetic energy 2 and potential energy at the outlet. Since that there is no elevation, we can neglect the potential energy. And if you make an analysis for compressor and turbine, people will usually just ignore the kinetic energy. It is because kinetic energy, the value is too small, so it will bring an insignificant change upon the final answer for the energy equation. So we just neglect it. But in this case, it is because the question doesn't state the volume, the velocity for the air. So that's why I'm neglecting it. So we can simplify this question into enthalpy 2, specific enthalpy 2 equal to, this would be plus and this would be plus, this would be minus. Work in, specific work in plus by enthalpy 1 minus by Q dot. It is referred to heat loss. So work in, it is equal to power over by mass flow rate. So this is the equation that you need to take note. So power, that will be 500 kilowatt over by the mass flow rate 2.9528. Thus we'll get 338.6616 kilojoule per kg. So enthalpy 2, it is equal to 338.6616 kilo. It is the value for enthalpy 1. I'm getting it from the table A17. Since that being state at the inlet, the temperature of the air will be 22 degrees C. So that's why we need to change into Kelvin, because this table will respect into Kelvin. We will get 295 at 295 degrees C. The enthalpy will be 295.17. So that's where I'm getting this value. The 318.6616, it is the work in plus by the enthalpy 1. So this is where I'm getting the enthalpy 1 minus by the heat loss 16 Kelvin. So we'll get 617.8316 kilojoule per kg for enthalpy 2. We need to make an interpolation because we cannot retrieve this value directly from the table. So that's why we make an interpolation between the temperature and the enthalpy. We need to take the closer value upon 617.8316 kilojoule per kg enthalpy. So we make an interpolation, thus we will get the temperature 2 equal to 610.28 Kelvin, and in the form of degree, there will be 337.28. So I think that's all for today. Thank you for watching and have a nice day. Bye bye.